basic ideas in probability. Under this section, we will talk about some fundamental rules in probability, and we'll talk about conditional probability, Bayes theorem, and permutations and combinations. What we'll do is we will introduce the ideas, and then we will talk about some examples and make sure that we are firmly grounded in these basic ideas before we move on to more interesting concepts in probability. Yeah. So again, we'll talk about some fundamental rules, then we'll talk about conditional probability, and then we'll talk about Bayes theorem, and then we will move on to permutations and combinations, which basically is it starts with the fundamental principle of counting, and then we'll move on to permutations and combinations and so on. Okay, great. So let's start with what is an experiment. Yeah, in probability, we have an experiment. An experiment is something that you can observe and measure. Okay, an experiment is something that you can observe and measure. So a simple example of an experiment will be when you roll a six-sided die, right? So, or you toss a fair coin. That is an experiment. Yeah. So by definition, right, an experiment is a process where you can observe outcomes. So I've given you the examples here where you roll a die, or you can flip a coin and you can observe whether it's a head or a tail, or whether the outcome is a 1 or a 2 or a 3, and so on. Okay, so an experiment is something that you can observe and measure. Great. S, right? Very important for us, right? S is the sample space, right? An experiment, right, has outcomes, right? When you roll a die, you can have either 1, 2, a six-sided die I'm talking about, right? You can either have a 1, 2, 3, 4, 5, or 6, right? So the sample space S, right, is the set of all possible outcomes. So when you roll a die, right, when you roll a die, let me say it again, right? S, yeah, is a sample space of an experiment. It's a set, very important word, set of all possible outcomes for the experiment. So rolling a die, 1, 2, 3, 4, 5, or 6. So this is your sample space, right? We have a set and it lists all the possible outcomes. Okay. Now that you know about a sample space, so what about the sample space if you flip a coin, right? So then it'll just be this, right? If you flip a coin just once, it's either a head or a tail. Okay, great. Now we want to go into the idea of events. Okay, what is an event? An event A, right, is a subset of the sample space. Again, remember what I said about the sample space, right? Always keep in mind, right, the sample space S, it's easy to remember it if you think of sample space, experiment, rolling a fair die, outcomes 1, 2, 3, 4, 5, or 6. Now, an event A, right, is a subset of the sample space. So, for example, I have, you know, event A here, 1, 3, and 5, right? You have 1 here, we have 3 here, and 5 here, a subset of the sample space. That's an event, right? So I've given you another example here where you consider tossing a coin 3 times and you look at the possible outcomes. So your sample space, I think you can figure this out yourself, right? You can figure this out yourself, right? And we have H, yeah? Head, H, T, right? Head, and tail, or you can have a head followed by a tail and followed by a head, and so on, right? So if you define, right, again, right, here I'm telling you that this event A is defined as the event of obtaining more than one head. Again, we are defining the event A, and we are saying that A is the event of obtaining more than one head. So more than one head, we are looking at this one here, we are looking at this one here, 2 heads, more than one, right? More than one. So we have this, and that's it, right? And that's it. So this is your event A. Okay, so important things: sample space, all the outcomes of an experiment. Okay, and then we have an event, the subset of a sample space, and now we want to talk about probability, right? So, folks, probability, right, gives you, I've written it down here, okay? It gives you a measure of the likelihood of an event, okay? Okay, probability, right, gives you a measure of the likelihood of an event. Okay, what is the likelihood of something happening? Yeah, what is the chance of something happening, right? So we like to define probability as the number of possible, excuse me, let me say it again, right? Probability of an event A, right? Maybe I should write it here. Probability of event A is a ratio. You look at the number of probable cases. I repeat, the number of probable cases divided by your number of possible cases, right? So if you want to make a comment about what is the probability of a particular song, yeah, hitting #1, yeah, on the weekly chart, then you must know how many songs are in the running for it. So that's what I mean by, okay, possible cases, right? So we have number of probable cases over number of possible cases. Now, we like to write it like this, where in mathematical notation, we like to say it's the number of elements in your set A. Remember what is set A? A is your event, right? So NA is the number of elements in your set A divided by everything. That is your number of elements in your sample space. There you go. Okay. So if you define, right, an event A, okay, if you define an event, let me say that again. If you define an event A, that means when you roll a die, right? When you roll a die, you are saying, let A be the event of a score more than 2 turning up. Let me say that again, right? You define an event A. What do? You roll a die, a die, right? A fair 6-sided die, and you define the event A as an outcome greater than 2 turning up. Okay, so this will be your outcome bigger than 2, right? So it's either 3, 4, 5, or 6, right? So this is your event A. Remember, it's a subset of your sample space. So the probability of A will be the number of elements in your set A, in this case is 4, and the number of elements in your sample space. Remember, we had 6 of those, so 4 over 6, and we are done. We're just assuming here that all the outcomes are equally likely. That's why I said a fair die, right? So all the outcomes here are equally likely. So we like to use this expression here, classical probability, right? Where we say that all the outcomes are equally likely. Okay, now that you know about your sample space, all the outcomes in an experiment, okay, a set of all the outcomes in an experiment, and then I introduce you to the idea of what do you call it? The event A, a subset of S, and then we introduce the idea of probability, right? Now, before we say anything else, right, please remember the probability of an event, right? I will say this again. I'll keep this as a common idea, right? It's a common theme that repeats itself. The probability of an event A is always, the probability of any event is always between 0 and 1. Yeah. So which means if your probability of an event is A, is 0, then we call it an impossible event. Won't happen. If the probability of an event A is 1, then it's sure to happen. Yeah, we call it a certain event. Okay. Now let's talk about the axioms of probability, right? So when you deal with the axioms of probability, okay, there are 3 of them, axioms of probability, and so let's talk about this. I just said the first one. Okay, let me just clear this. Okay, great. So we have got for any event A, I just said this, right? Probability of an event A is always between 0 and 1. Yeah, for any event A. So that's your first axiom of probability. And the second axiom, different books write this differently, right? But basically the idea that they want to convey is the same, right? So the probability of your sample space is 1. Yeah, one of it must happen, right? One of it must, when you conduct an experiment, one of the outcomes must appear. So the probability of S is 1. Next one, the third one. Yeah, if A1 and A2 are mutually exclusive events. Yeah, what are mutually exclusive events? Mutually exclusive events are events that cannot happen together, right? Let me say it again. Yeah, mutually exclusive events are events that cannot happen at the same time, right? So you cannot be sitting at your table reading a book and being out of your house watching a movie in the theater at the same time, right? So they are mutually exclusive. So if A1 and A2 are mutually exclusive events, then that's what I meant. That's what I mean by this, right? A1 intersect A2. That means A1 happening at the same time as A2. It cannot happen, right? It cannot happen. So we call it a, what do you call this? This is called a null set. Yeah. So I'll tell you again, mutually exclusive events are events that cannot happen at the same time. I gave you a classic example, staying home and reading a book and going out for a movie. It cannot happen at the same time. So we call the intersection of A1 and A2, if they are mutually exclusive, we call it, this thing is called a null set, right? A null set. So it cannot happen. Now, when you say, if you're not sure what a null set is, a null set is a set which has got no elements in it. Okay, there are no elements in it. So what is important for us? The fact that A1 union A2, okay, the probability of A1 or A2 is probability of A1 plus the probability of A2. Very important, yeah? For mutually exclusive events, okay, the probability of A1 happening, let's use the A1, right? The probability of A1 happening or A2 happening, that's what this means. That's what this means, union, right? A1 or A2 is probability of A1 plus probability of A2. Again, let me say it again. Probability of A1 union A2, probability of A1 union A2 is probability of A1 plus probability of A2. So those are very powerful ideas. So make sure you know those things. Yeah, it's important in the learning of probability. So we want to note a corollary just to extend it a little bit. Yeah, to extend it a little bit. If there are n mutually exclusive events, then this follows, right? A1, probability of A1 union A2 union A3 right up to union AN. So A1 or A2 or A3 or any of these happening, right? Okay, probability will be equals to add up the individual probabilities, right? Add up the individual probabilities, probability A1 plus probability A2. This is just an extension from the previous idea. The previous idea, it was just two events, two mutually exclusive events. Now we're just extending the idea to n mutually exclusive events. Okay, so let's look at this example, right? We want to roll a fair die once. Yeah, a fair die, right? Look, some of you might use the word dice, right? Okay, I will use the word one die, okay, and two dice. Yeah, okay. So we are defining A1. Watch carefully. We are defining A1 as an outcome, right? It's either 3, 4, or 5. Again, let's define A1, the event that the score, right, that you get when you roll a fair die once is either 3, 4, or 5. Okay, and A2 is the event that the score that you get is 6. Now, if you don't like the use of the word score, you can also use the word. You can also use the word. You can use the phrase rather. The number that is uppermost on the die is 3, 4, or 5. In this case, it will be 6, right? So we have defined A1 and A2, and note A1 A intersect A2, right? Let me write it here. This one here is A1 intersect A2, right? Some people like to call it A1 and A2. Okay. Now, so remember I told you something about, look at the elements here, right? 3, 4, or 5. This is 6. So you know that if A1 happens, A2 cannot happen, right? If A1 happens, A2 cannot happen. Therefore, they are mutually exclusive. So, okay. So we have A1 intersect A2. Okay. That means A1 and A2 happening at the same time. I repeat, A1 and A2 happening at the same time is not possible. So we have a null set, right? and the probability of a null set is 0. Okay, there are no common elements. Okay, now what is the probability of A1? That's easy, right? A1, look at the number of elements here, which is 3. Okay, and A1 over NS, right? That was the definition we had. So this will be what? 1, 2, 3 over 6, and we are done. Okay, I mean, I didn't write 1 over 2. You can write it yourself, right? A2, easier still. There's only one element here, so it's just 1 over 6. Okay, now remember, they are mutually exclusive. So if we define our event A as A1 union A2, okay, then you know that your A will be all the elements in A1 and all the elements in A2. So this is your set A, or event A if you like. So the probability of event A will be mutually exclusive, so you can just add them up, right? This plus this, right? Remember, if they're mutually exclusive, A1 union A2, the probability will be A1 plus probability of A2. So I've done it here, and you can get your answer 4 over 6, or you can simplify the 2 over 3. So important ideas, right? They are important ideas, and you don't want to miss them, right? Okay. The other thing is, I want to introduce you to the term, the complement of an event, right? A prime. So A prime is the complement of event A, right? So what is A prime? A prime is not A. That's basically it, right? What is A prime? So let me clear this. Okay. What is A prime? This one. Okay. This one here. This is A prime. A prime, right? It's the complement of A. What it means is A prime is not A. So if A is the event, right? If A is the event that it will rain today. Okay, let's say A is the event that it will rain today. So what is A prime? A prime is the event that it won't rain today. That's it, right? So if A is the event that he's going to buy a black car, well, color black, yeah. Then what is A prime? What is A prime? He's going to buy a car which is not color black. That's it, right? So it's just not A. So what is important here? Probability of A prime is 1 minus probability of A. Okay, so this is very important. So I try to tell you this by way of an example here, because we had this example a few lines ago. So I have A, which is 3, 4, 5, 6. So what is A prime? What is not A? This one, right? Right? If A is 3, 4, 5, 6, A prime must be 1 or 2. Okay, this set A prime must have these two elements. So what's the probability of A prime? 1, 2, 2 over 6. Correct? Which is 1 minus 4 over 6, and everything works out well. Okay, so please remember, probability of A prime is 1 minus probability of A. Now, having said all that, we want to quickly look at some pictures which are called Venn diagrams, and we'll breeze through this. Okay, Venn diagrams. And what are the things that you want to observe, right? Okay, you want to observe a few things here. First, this rectangle thing, right? This represents your sample space. So sometimes I might not even write it, right? This rectangle thing here represents the sample space. I've indicated here, yeah, on my picture. Sometimes I don't write it, so you can go and write it, right? So it's accepted that the sample space is indicated by a rectangle. Okay. Nowadays, people do other things as well. Okay, but I think we'll stick to this. Now, inside your rectangle, we are going to have sets. Remember, events are always subsets of your sample space. So let's deal with A first. Just, okay, an event A is represented by a circle. Okay, an event A is represented by a circle. If you want to say it another way, this circle here represents an event A. So if this circle represents an event A, which means if you stand inside here, A is happening. Okay, if you stand outside here, A is not happening. So that will be what? A prime. So let me shade that. Yeah. So this will be A prime. So inside the circle is A, outside the circle is A prime. Easy? Yep. So if you have the second idea, right? If you have mutually exclusive events, yeah. If you have mutually exclusive events, Remember, they can't happen together, right? Okay, so which means they cannot intersect. So we indicate mutually exclusive events like this: one event A and one event B. Okay, they cannot intersect. They cannot happen at the same time. Good. What happens if they can happen at the same time? Well, then there must be some intersection, right? There must be some intersection. So let's look at this. A intersect B. So when they can happen at the same time, okay, then you have, this is what we mean by the two circles intersecting. And this region here that I've shaded represents A happening and B happening. Careful, right? If you don't like that, you can say A happens and B happens in this shaded region. So the notation is A intersect B, right? Okay, then we have A union B, A or B or both, right? Union, right? A happens or B happens or both happen. Okay, so remember, right? When you're dealing with mutually exclusive, this can't be true, both can't happen. So you stick to A or B. So this region that is shaded here is, you can either be here, you can be here or here, right? A happens and B doesn't happen. B happens and A doesn't happen. Or here, A and B both happen. So this whole thing that I've shaded here represents A union B. Okay, A happens or B happens or both happen. Okay, and just to add an example, I shaded this region here. Make sure you know this, right? If you stand here, B happens and A does not happen, right? Let me write it here. B happens, okay, and A does not happen. Okay, so this thing is important. Yeah, B happens if you stand here and A does not happen. So we have this thing, B intersect A prime. Okay, so that's pretty good, right? I think that Venn diagrams help us, right? When we sometimes look at some questions in probability, Venn diagrams help us to deal with them quite quickly. Okay, next, let's look at the formula probability of A union B. Okay, okay. Some books have some other derivations of these formulas, but let's just look at the logic of it, right? So watch, we are looking at, okay, we want to write the formula for probability of A union B. And what did I say this means? A happens, or B happens, or both happen, right? So how do you take care of this, right? So we have one circle here, okay? We have one circle here which represents A. So let's write that down. A plus, there's another circle here that represents B. Hey, I added this twice, right? So I take it off once. That's it. So you see this formula coming up, right? So that's very useful for us. Okay, very useful for us. One of the books sometimes call it the general addition rule and so on. I'm not going to all these rules and all that, right? We want to understand the ideas. So A union B is A plus B minus A and B. Did you get that? A union B is A plus B minus A and B. So you just have to fit in the probability, the letter P there, and you'll get this this formula that is kind of fundamental, right? I have written all these things here. Okay, so now let's move it up a little bit. Okay, move the screen up and then let's follow along. Okay, basically what I've done here is some examples to talk about what we just discussed, right? Like some of the, what's the word for it? Some of the rules of probability, some ideas connected to Venn diagrams and so on. So if you look at this, right? What have I written here? Let me clear this and then we will follow along. Okay. So what did I say here? I said roll a fair die, fine, and say you define the event. You have to define the event, right? You define the event so that you and I are talking about the same thing. So define event A, an event of getting an odd number. So A is the event of getting an odd number, yeah, odd number. So your subset will be 1, 3, 5, right, of your sample space. So the probability of A, easy, eh? 3, 1, 2, 3 divided by how many? 6. That's it. Okay, you can write the half in. Now, let's come back here and look at what I have written here, right? B, I'm going to define B as the event. B is the event that you get a number 3 or less. So what are the elements in your set? B, 1, 2, 3, right? Okay, so this probability is also 3/6. Yeah, probability of event B is also 3/6. Okay, now A union B. Now remember A union B, right? It's either A happens or B happens or both happen. So A union B, your set, right, must have, your set must have this, this. What else? 1 and 3 is already here, and this number. There you go. 1, 2, 3, and 5. Okay, so it's not hard, right? A happens or B happens or both happen. So 1, 2, 3, 5, the probability of A union B will be what? 1, 2, 3, 4/6. Okay, now A intersect B, well, we are here, let's settle this. A intersect B, it must be in A and it must be in B. What's in A and B? 1 is here, 3 is here. That's it, right? So A intersect B is just, it's just a set which has elements 1 and 3. What is the probability of A intersect B? 1, 2, 2 divided by 6. So it's not hard, right? It's not hard. So it's just a matter of getting the ideas right, and you can move on. Now, why did we go through all this? Because I want to tell you this. This is known as the general addition rule, right, in probability. And so I'm just plugging in some. What's the probability of A? I gave you. What is the probability of A? 3/6. What's the probability of B? I gave you as well. 3/6. There you go. Remember, A union B is A plus B minus A and B. A and B is what? 2/6. So if you look at these numbers here, 3 plus 3 is 6 minus 2 is 4, and you see it jives with this answer. So it makes perfect sense, right? Okay. One more thing that I like to add here is this. Yeah, watch carefully. I'm going to draw a picture. Okay, I'm going to draw a picture. I'm not sure whether it's there already. If it's there, then we can use it. Otherwise, I will draw the picture. Okay. Now, okay, great. So let's say we have, look, I'm not drawing in the sample space, right? Some people call the sample space the universe. I'm just using A and I'm using B. Okay. So what's the big deal here? I'm looking at probability of B. So basically, I want this, right? Now, this thing here is made up of 2 portions. Yeah. Probability of B is what I've shaded here. And you can see it's made up of 2 parts. This part here, what is this? Yes. Probability of A and B, right? A intersect B. And what is this? Let me just, what is this? This one is B happens and A does not happen. There you go. So you can write the probability of B as probability of A and B plus the probability of B and not A. Okay. So you'll find these things quite useful. I have shown this picture to you somewhere in the middle of the page earlier, right? So that's pretty good. Now, let's look at an example, right? So we have, okay, let's read the question, right? Let's read the question. Great. This is an old exam question, right? A variation of the Society of Actuaries probability exam. Okay, you can find it on the web and so on. I use the question to indicate an idea. The probability, right, that a visit to a primary care physician, okay, the office of a primary care physician, yeah, PCP. So the probability of a visit results in either lab work or referral to a specialist. So understand the idea in the question first, yeah. So the probability that a visit to a primary care physician's office results in either lab work or referral to a specialty is what? 60%. So be very careful about this, yeah. Be very careful about this. I need to tell you to read the question again. the probability. Remember, they're giving you the probability. So where is it, right? You'll be looking for it. Oh, there, here it is. And what does that indicate to you? That a visit to a primary care physician's office results in either lab work or referral to a specialist is 60%. Either this or this. Okay? So the probability of either this or this is 0.6. This is 0.6, yeah? Now, of those coming to a PCP's office, 35% are referred to specialists, okay? And 50% are 50% require lab work. Again, of those coming to this office, this PCP's office, 35% are referred to specialists and 50% require lab work. Okay. Now, what is the question, right? Once you read a question in probability, what you do, you keep these things in perspective, right? Very clearly, right? What is going on. So when you go to this doctor's office, you can get either, lab work done or get referred to some specialist with a certain probability. And then of those coming to the office, 35% are referred to specialists and 50% require lab work. Now they ask you to find the probability that a visit to a PCP's office results in what? Both lab work and referral. So here we had a case of or. Here we had some individual probabilities, and here we have both. So keep these things in mind, right? Both lab work and referral to a specialist. So I have written a solution here. You can shorten the solution if you like, but it's more of a teaching solution. So I have written this in quite detail. Okay, great. So let me clear this. Let's look at what I've done. Yeah, L. I've defined L, right? Okay. By the way, this solution you can, like I said, right? You can write shorter notes to it. L is the event that a visit to the PCP office requires lab work. Okay. L is the event. Why do I use L? Because lab, right? So L is the event that a visit to the PCP office requires lab work, and S is the event that a visit to the PCP office requires reference to, or rather referral to a specialist. So what I write here, event that a visit to the PCP office is referred to a specialist. So I use these letters, right? S and L. Okay. This one they gave me in the question, 60%. Either lab work or referred to a specialist. The probability is 60%. They gave me. So it is L union S is 0.6. This also they gave me. The probability of being referred to a specialist is 35%. They gave me. Okay. And requiring lab work, the probability is 0.5. This also is given. Now, this is what they want. Okay. Somebody going in to visit, somebody going into the PCP office requires both lab work and referral to a specialist. So you want to find the probability. Okay. L intersect S. Okay? This is L intersect. You want to find this. Use this formula. Easy. L union S is L plus S minus ln S. So, just clean this up a little bit. Do some minor algebra, bring it to the left-hand side, move this to the right-hand side, and you'll get a nice answer. Okay. The important thing is to write down the information that they give you in the question, and then using some formula. Some people like to use A and B for the events, but that's fine. Okay, that's fine. You can do that. Okay. Then there's this example here, somewhat similar. Okay. Let's read that. Yeah, let's read that. Let me clear this. Yeah, so that you can see. Okay. We can go a little bit faster now because you know the basic formulas already. Okay. Among a large group of patients, right, recovering from shoulder injuries, it is found that 25% visit both a physical therapist and a chiropractor, right? So this thing here is a probability, and take note of this: a physical therapist and a chiropractor. 85%, right? 85%, they visit at least one of these. At least one means what? Either the physical therapist or the chiropractor or both. So that will be what? Union, right? Okay, good. The probability that a patient visits a chiropractor exceeds by 0.2 the probability that a patient visits a physical therapist. Okay, the probability that a patient visits a chiropractor exceeds by 0.2 the probability that a patient visits a physical therapist. So what are we asked to find? The probability that a randomly chosen member of this group visits a physical therapist. So read the question carefully, understand what they're saying, and then you have to write it down in the form of notation. Use notation rather, maybe that's the way I should say it. Use notation that you're comfortable with. So I wrote, okay, PT, yeah, the event that you visit a physical therapist, yeah, PT. And then C, of course, yeah, chiropractor. Now, these numbers are all given to me, right? The probability of visiting both a physical therapist and a chiropractor is 25%, so 0.25. Either a chiropractor or a physical therapist or both, they gave me 0.85. And that is this thing here, PT union C is 0.85. And then they gave me a line here about the probability of visiting a chiropractor exceeding, yeah, the probability of visiting a physical therapist by some amount, which is 0.2. So I wrote that here as well. Probability of C minus probability of PT is 0.2. Now we're asked to find the probability that a randomly chosen member of the group visits a physical therapist. So we're trying to find this. So that's the key to this probability, right? You must look at the question, read it carefully, and then write it in the form, use some notation that you are comfortable with. Some people just stick to A and B, right? I've used PT for physical therapy, it's easier for me to refer to it, and C for chiropractor and so on. The rest of the question, right? You know what you're trying to find. It's not hard at all, right? Once you get all this out of the way, then you'll find, hey, this is something that you can easily work, right? You can easily work. So if you look at this, right? Okay, let's go through this, yeah? This formula, you know, PT union C, okay? PT union C will be PT plus C minus PT and C, right? Remember, A union B is what? A union B is what? A plus B minus A and B, right? So this is just PT union C, just replace all those things. Now, you have all these numbers, right? You can easily plug in here. You know, this one you have, right? 0.85, right? Okay. This one you have, right? How much is it? 0.25. So this thing here, if you bring this to the left-hand side, it'll be what? 0.85 plus 0.25, you'll get some number, one equation. The second equation, I've shown it to you here. Just solve it, yeah? That is easy for you. Clean that up a little bit, and you'll get the probability of a randomly chosen member visiting a physical therapist will be 0.45. This is the important line, and this is the other important line. You can solve in simultaneous fashion, and that's it, right? We don't want to deal with simultaneous equations now. It's too easy for us, right? Okay, next one. Okay, next example. Let's move on. I want to tell you about, okay, this Venn diagram thing, right? I think it's a powerful idea, so let's just discuss it, right? Okay. We are defining an event A that Alan is busy, okay? A is the event that Alan is busy, and B is the event that Bob is busy. Okay, you got the idea, right? Great. Now, A is the event that Alan's busy, and B is the event that Bob is busy. Good. Now, what happens is, given they gave you these probabilities, okay? They gave you all these probabilities, yeah? A is busy, Alan's busy, Bob is busy, both Alan and Bob are busy. Find the probability, careful, that neither Alan nor Bob is busy. So we are looking for what? The probability of not busy and not busy. Okay. So Alan not busy and Bob not busy. That's what you're trying to find. So I can give you a formula straight away. Yeah, I can give you a formula. Okay, this thing here. Take a look at it. Right. I can give you this straight away. Okay. But I like you to look at the picture and appreciate the picture. Right. So remember this thing here. Let me just shade it in red. Right. This one here is A union B. Right. Let me write it here. This is A union B. So this thing here outside this two circle, right? So this thing here, right, which I've shaded here, okay, is your A not happening and B not happening. So which means it is 1 minus probability of A union B, right? Because this is S, right? S is the probability of S is what? 1, correct? So it is 1 minus. So you can write probability of A prime and B prime is this. So now that we have it, okay, we need to find this. That's easy to find because, you know, they gave me all the facts. I have A, I have B, and I have A and B. So that's easy. I've done it here for you, right? I have A plus B minus A and B. I get this. So 1 minus 0.44 is 0.56. Okay. So I want to move on a little bit and show you a couple of examples dealing with Venn diagrams. Okay. Let's start slowly. Yeah. So I will move a bit slowly on the next page. Get the ideas. Yeah. Get the ideas. Okay. So now let's read the question, right? Okay. Let's clear. Okay. Good. Now I have a survey, right, of a group's viewing habits found the following. Okay. 31% watched gymnastics, 25% watched baseball, and 21% watched soccer. So keep these numbers in mind, right? 31%, 25% baseball, 21% soccer. Okay. What are we doing? There's a survey and we're looking at the viewing habits, yeah, what they watch. 11% watch gymnastics, very important word, and baseball. 8% watch baseball and soccer. And 9% watch gymnastics and soccer. So careful, right? And 5% watch all three. Okay, watch all three. Now, you're asked to find the percentage of the group that watched none of the three sports. Okay, they did not watch gymnastics, they did not watch baseball, and they did not watch soccer. So what you do, you use your Venn diagram, right? Use a Venn diagram to your advantage. Set up a Venn diagram, draw a little rectangle. Because you have gymnastics, what is the other one? Gymnastics, baseball, and soccer, right? Yeah, gymnastics, baseball, and soccer. So you must have 3 circles at least, and they all intersect. So put all those in a Venn diagram first, and listen to what I'm going to say next, right? Always fill in the innermost first. That means watched all 3, yeah, where all the 3 circles intersect. So let me show you that, right? Let me show you that. Okay. Okay, good. So let's start here. Okay. And keep an eye on the numbers, right? You can follow the solution quite easily. Remember, what did I tell you? When you have a Venn diagram problem like this, start with where all the circles intersect, right? So we start with this number here. Okay, 5% watched all, what do you call it? All 3 spots. You start in the center and then you move outwards. Okay, good. Now, and then keep in mind what they're asking you to find. They're asking you to find the percentage of people who watch none of the sports. Okay, so this G represents my one event, gymnastics. This B represents my one event, which is what? Baseball. And this S is for what? Soccer. Okay, so all the 3 circles represent all the 3 sports. You start here and then you start filling out the intersections. Remember, we have got 11% watch gymnastics and baseball. So gymnastics and baseball, can you see? This is the part. I'm not going to clutter this up, right? Maybe I should just put an arrow, yeah? 11% watch gymnastics and baseball. Okay. And then 8% watch baseball and soccer. Can you see this one? Okay. And then how much? 9% watch gymnastics and soccer. This one. Gymnastics and soccer. Okay. This is gymnastics and soccer. So now that you have 5 here, right? You can fill this out. 4. 5 plus 4 is 9. Then 6 plus 5 is 11. And then 5 plus 3 is 8. Done. Okay. once you're done with that, right? I've given you all the ideas here, right? 11 minus 5 and so on. You can easily do that. Then you go and look at the individual circles. How many people watch gymnastics? 31, right? 31. So how many have you taken care of here? 4 plus 5 is how many? 9. 9 plus 6 is 15. But 31 watch gymnastics, right? So 31 minus 15, 16. So you plug that number in. Let's do baseball, right? 25% watch baseball. So I have 3 here. I have 5 here, 8. 8 plus 6 is 14. So 25 minus 14, 11. Taken care of. So that's how you solve or rather work out problems like this. Plug in all the numbers. Yeah, you can easily do this 9 yourself. Yeah, which is 21 minus 4 minus 5 minus 3, and you'll get 9. Okay. Now, once you've done that, once you've done that, right, you need to look at all these numbers, right? This number here plus this number here plus this number here. Okay. And then this number here, this number here, this number here. Okay. And this number here. I'm adding up all the numbers. Okay. I'm adding up all the numbers. Careful about this. Yeah. Don't miss out any number and don't add twice. So I'm adding this, and this. And I'll get how much? 54. So 54% is contained in all these 3 circles. So how much is outside? So outside the 3 circles will be what? 100 minus 54, which is 46%. And we are done. That's it, right? So that's a good example to pick up some ideas on what's the word for it? Venn diagrams, right? The use of Venn diagrams when we try and deal with probabilities. Now, let me just do one more example. Okay, here, connected to Venn diagrams. Look at the question, right? Look at the question. The same idea. You can sort of figure this out. I just give you some help. An insurer, right? An insurer offers a health plan to the employees of a large company. As part of this plan, the individual employees may choose. Careful, right? The individual employees may choose what? Exactly 2. Exactly 2 of the supplementary coverages A, B, and C. Okay, watch carefully, right? Let me just underline this, right? So read the whole question first, then you can solve the problem. As part of the plan, the individual employees may choose exactly 2 of the coverages A, B, and C, or they may choose no supplementary coverage. Got it? Let me clear this again so you can see it. Okay, so you can choose exactly 2, or you choose none. The proportion of the company's employees that choose A, B, and C are given. Yeah, they gave you this. Okay, you can see they add up to 1, right? This is what 3 over 12. This is what 4 over 12, and this is 5 over 12. Okay, great. So what are we asked to find? The probability that a randomly chosen employee will choose what? No supplementary coverage. So you do the same thing like we did earlier, and you can work it out. Okay, not a problem at all. Okay, let me just show you what I've written here so that you can sort of follow along easily, right? Let me just show you. Okay, now that you know the question, right? Maybe I can move it up. Okay, great. Okay. The last line there is a formula, so that formula you can easily look it up on unions of 3 events. But let me come back to my problem first, right? So draw the 3 circles, right? Draw the 3 circles. I've done it here for you. Draw the 3 circles. Okay. And remember what I said? Start by placing what? This thing, where all the 3 intersect. Okay. Can you see this one? Okay. So remember, you also choose 2 or none. That's in the question. You either choose exactly 2 or none. Okay. So you just plug in all these numbers. I've used an X here and all that, so you can see how I have started. Okay, you can go through this slowly, right? Because A, B, and C, just write down the probability so that you don't miss anything. A is what? 1 over 4. Okay. B is what? 1 over 3. And C is what? 5 over 12. Okay. So why is this 0 here? This is 0 here because you know what? They have to choose exactly 2 or none. So you can't be standing here. Okay. All right. So you can't be standing here because you have to choose 2 or none at all. That's why you find this is 0, this is 0, and this is 0. Okay. And we have got, I placed some x's here so that I can write some equations, right? And you can see how I get all this. Okay. I have 5 over 12 here is 1 over 4 minus x plus 1. You know, you clean this up, this algebra, right? You can see, okay, 1 over 4 minus x where I got this, 1 over 3 minus x where I got this. I've indicated that for you here and here. Okay, I've indicated that for you. And then you solve for x, you'll get something here. And then you just add up, right? For all the 3 circles, you can add this up and you'll get 6 over 12. Not hard to do, right? Just plug in all this. And then remember, we are adding up to get a value of 5 over 12. And then solve for x, you'll get 1 over 12. And then you find that you want to find, what do you call it? The probability that this guy is going to choose no coverage, right? So outside the circles. So if inside the circles, the total is 6 over 12. Okay, if inside the circle is 6 over 12, outside the circles must also be 1 minus, that must be 6 over 12, which is a half. Okay, so pause the video and look at it and make sure you understand how I got these numbers. Yeah. Now, this last line there is a formula for 3 events. Let me just see whether I can. Yeah. So I think this should be, I don't need to talk about this at all. The last line here is a formula. Okay, let me just clear this. Yeah, just give me a second. Okay, good. For any 3 events, right? A, B, and C, if you ask to find A union B union C, I repeat, I normally speak like this, right? A union B union C. I sometimes forget to say it's a probability, right? So anyway, the probability of A union B union C, A or B and C, all those things, right? Now, for us, this thing here is given as a formula in some books, A plus B plus C minus the intersections and plus something, because you can actually follow the logic that I gave you earlier and arrive at the same formula. You add all 3 circles and then you take away some. Okay, you add all the 3 circles. Okay, you add all the 3 circles and then you take away those things that you added twice, and then hey, you took off something too much, so you have to add that back in. So this is a formula that you find in many books, and I think that is very useful in some probability calculations. Yeah, just keep that in mind. But do you need to memorize this in when you study probability? Not really. If you draw these circles, you can get this out yourself. But there are some people who choose to memorize this. You draw these circles, you can get this out without any problem. Okay.